Okay, I'm just going to give it 1 minute till the top of the hour here, and then we're going to kick it off. Okay, everyone. Well, thank you very much for joining our great Denver Hyperledger meetup here. This is the fourth in a series of virtual meetups that we've done, and I'm really excited about this meetup. We've got some great speakers and presentation today. We've got Eugene from Intel that's going to talk to us about Hyperledger Avalon. And then we also have another local Denver person, which is Keenan Olson from Chainlink that's joined us today. So let me give you a little bit of background on Hyperledger Avalon. It's really talking about the trusted compute specification, and Eugene is really the lead architect here and is collaborating with the Enterprise Ethereum Alliance on this. And really, Eugene is an architect that has over 20 years of experience with Intel. He's designed and built a number of distributed and decentralized solutions and worked on embedded firmware to large-scale cloud solutions. And really now he's focused on scalability and confidentiality for both public and private blockchains, and definitely focused on utilizing this trusted execution environment for off-chain workload execution. He's the co-author of the Enterprise Ethereum Alliance Off-Chain Trusted Compute Specification, and really the lead architect and maintainer of Hyperledger Avalon. So at this point, I have the pleasure of turning over the meetup to Eugene, and then what we'll do is see what else from Chainlink we can cover, and then we'll go ahead and hold the Q&A for the end of the session. So at this point, Eugene, I'm going to turn it over to you and take it away.
Thank you, John, and hi, everybody. It's great to have an opportunity to present the Avalon at this virtual meetup. Hopefully, we're going to have at some point not only virtual meetups. Okay, and now I have to figure out how to. Okay, so today we're going to talk a little bit about what is Avalon at glance. We're going to touch on the confidential compute and trusted execution environments. Since this is the foundation of what we're doing, and it may be a little bit new topic for some of you, when we talk about the background and usages that we focus in the Avalon and what kind of challenges we're trying to address, and then we'll move to the architecture of the project. So fundamentally, we all know that the scalability and confidentiality is the big part of the blockchains, and that is not, and it's a complex issues that is hard to address. So what we're trying to do with Avalon, we're pretty much saying that let's do the execution off chain, and at the same time, like they say, we want to have our cake and eat it too. So for that, we will utilize the trusted execution environments. So in this case, we can extend the computational trust beyond blockchain and don't have to rely on the institutional trust in order for the trust to the outsource the data. So the key that our Avalon is actually running side by side with blockchain, and it's blockchain neutral. It can work with different types of blockchains. Currently, we have support for the Ethereum and Fabric. If you look on the right-hand side, the Hyperledger greenhouse, you will see that Avalon is not a blockchain. It's a tool that runs the side by side with Avalon. And as the John already mentioned, that we do rely on the Enterprise Ethereum Alliance specification called Off-Chain Trusted Compute. And that is actually the specification that we implemented in our project. And we believe that standard-based approach is better than just ad hoc approach. The project was actually sponsored by 16 companies and organizations when it was introduced as the top-level project to the Hyperledger organization. You can see the list on the right-hand side. And to my knowledge, this is currently a record number for any project within the Hyperledger organization. And finally, I have a few links here that you can use to get the more information about the project. So before I start to talk really about the Avalon itself, I would like to focus first on the what is actually foundation for our project, and that is the confidential compute and trusted execution environments. If we have any sensitive information, we definitely want to protect it. And it was kind of common to protect that for quite a long time at rest and in transit. That is actually well-known areas, and they have been for years, if not decades, in works. What is actually new frontier now is actually protecting data in use when they being computed, and that is actually the confidential computing, really about the protection data in use during the computation phase. In specifically, there are many different ways to protect that. You can use the MPC or zero knowledge. In our case, we rely on the hardware-based trusted execution environments that allow us more universal algorithms to be executed at relatively low cost of the computation. And it's particularly important to use this type of protection when you run your workloads on a platform that you don't control directly. So there are three kind of like parts in my mind related to the trusted execution environments. It's a secure enclaves, memory protection, and attestation. And I'm going to briefly go through all of them one by one. So first of all, the enclaves, and I will use the Intel SGX as an example, but the model effectively the extended to different trusted execution environments as well. So what we want to protect from a number of attacks. We want to protect from the malicious insiders that may be at the hosting service. We want to protect from the external attackers, and we want to protect from the third party without consent. All these can be done using the trusted hardware assisted or hardware based trusted execution environments. So the important part when it comes to SGX enclaves, that application can start the enclave at any time in user mode. And that enclave is really the memory specifically allocated that is not accessible by other part of the software running on this platform. And protection is done by the CPU itself. So the key here that protection is not only from this application on other applications, also the protection against the privileged code running in the operating system and in virtual machine manager, for example. It's also important that this um, protection mechanism can be use the extendable attestation mechanism, and it can be verified by remote party. We will talk about that a little bit in more details later. So another important part is actually is utilizing the memory protection outside of the CPU. It's not only protection against the software, but also the data they are unencrypted and known to the CPU only. They clear only the inside of CPU. The boundaries is the security perimeter is the CPU package. And whenever the data is sent outside of the package, they encrypt it. That is substantially increases the likelihood that external memory access is going to see only encrypted data. So this is another part of the protection that we rely and in our implementation. Now it's all this great. Let's say that the enclave has been started. It actually runs as supposed. It runs right code. But how we, a remote party, can really know that what is being executed is actually what we want to be executed. So we, in this case, we rely on the attestation that provides us with proof that of the code integrity and the authenticity. So first of all, we deploy the code on the remote platform. And at this time, the platform is actually measure the code, and the code can be also signed. This information is available done in the CPU, and it's not controlled by other software. The next step is to sign the attestation, again done at the platform level, and submit this information for the verification to the requester. That submitted information includes the number of pieces of information. So first of all, it actually confirms that the execution happens on the right hardware platform that has SGX on it. Secondly, it actually provides at what version is the TCB of that platform. TCB is the Trusted Compute Base, which is actually opcode and the firmware running in the CPU. And then it actually provides number of information about the code being loaded in that specific enclave. That is the value, which is called MR enclave, which is essentially a hash of the code loaded in the enclave. It also includes the signature of code if it's provided by the author of the code. So you can verify that who actually provided that code. And finally, there is an extension mechanism that allows us to extend that and use that for our specific purposes. And we will talk about that later when we're going to talk about the architecture. And finally, what we do, we can now at this time extend the secrets, exchange secrets between the trusted execution environments and the remote platform and trust the results. And that model allows us to protect the keys, protects the code, for example, scripts and models, and also it protects input and output data. So this is the foundation, confidential compute foundation that we are relying on to get our job done. So now let's talk a little bit about the usages. Before we go to specific usages, kind of like the conceptual view how we approach that. So we all know and love blockchains. If two enterprises want to communicate through the blockchains, what they do, they submit their data and the information, and they agree to execute the smart contract and trust those results. The results and execution, everything can be recorded on the blockchain. That is great, but it's not always how the enterprises want to communicate. In many cases, they don't want or they cannot share the information on the blockchain. So that is the how Avalon comes to play. So what we do, we actually introduce a new entity, Trusted Compute Service. It's shown as a separate entity in this picture, but technically it can reside either in Enterprise A or with Enterprise B, or there can be multiple Trusted Compute Services. So in this case, A and B can execute a smart contract at the Trusted Compute Service. The important part that, like we talked before, the attestation comes to play. The both Enterprise A and Enterprise B can trust that right code and right protection in place in the Trusted Compute Service, and they can trust two results. They can also, there are two paths of execution. They can submit their request and get results either through blockchain, or they can send them directly to the Trusted Compute Service. And the later is actually can be useful to decrease the stream of the transactions and keep them manageable for the blockchains. Also, in some cases, the regulations may not allow to release the data on the blockchain. But in any case, blockchain plays an important role because it maintains information about the trusted compute services available and workers, their effectively extended attestation information, and it also maintains the receipts, cryptographic proofs of the work being done in the trusted execution environment. So we can actually use that receipts for auditing and payment processing, or for the conflict resolutions. So now let's look at the couple more specific examples. So first of all, let's look at the IoT example with edge sensors. On the left-hand side, we have a warehouse that can have multiple sensors. And those sensors like temperature, humidity, they send their data directly to the blockchain. So in this case, in real world, the blockchain can be quite easily overloaded, or we have substantially throttled the stream of the data coming from the warehouses. So moving to the right-hand side, this is where the Avalon, it's called here the edge server, can be used to make processing more efficient. So the sensor data still accumulated locally at the warehouse and kept in the as a log. And edge server, in this case, submits only periodic updates to the blockchain. It can submit them, for example, once an hour or once a day, and saying that the warehouse is in compliance. Or if there is some kind of deviation, it may report that deviation as well. And the blockchain will maintain a receipt that includes the cryptographic proof of the all recorded data for the reported interval. So if necessary, the detailed log can be received and it can be verified against the receipt on the blockchain. This primary goal of this usage is the scalability to decrease number of transactions per second generated and sent to the blockchain without breaking the trust in the execution. Another example is mostly focusing on the privacy and the confidentiality. So let's imagine that there is a business, and that business wants to get the insurance quote from an insurance company for its employees, and it has this business has a healthy pool of employees. So they want to make sure that they get appropriate discount. So what they do, they authorize medical data access for the specific requests of the creating a quote by the insurance company. Then in step 2, they request the quote through the blockchain. And that quote is actually received in step 3 by the insurance company. Now insurance company is actually in the process wants to calculate heart disease risk factor and use that as a part of their assessment to provide the quote to the business. So there are two type of TEs shown on this picture. So insurance company starts execution in its own trusted execution environment, and it calls to the hospitals to process the data for the employees that is actually have records at the corresponding hospitals. In the practical case, most likely it's going to be multiple hospitals. At the step 5, the hospitals will get the authorization that they actually can run this request. It's important to understand that in this case, the TE relocated at hospitals may be used to protect code, because now in addition to the model when data goes to the code, there is a model when code goes to the data, because hospitals in many cases cannot release their medical records even in encrypted form to other parties. So that is why they have to do local processing. But at the same time, insurance company may want to protect its IP, its algorithm that they use to protect this data. And that is where the TE running at hospital will be very helpful. And after that, intermediate results submitted to the insurance company, and insurance company process them also in the trusted execution environment, making sure that even through the intermediate results, it cannot actually infer any information about the employees. And after that processing, the insurance company submits the quote to the business through the blockchain, and blockchain receive the quote. And if they like the quote, they just go with this quote or with this insurance company, or they can go to another insurance company and request another quote. So Since we're talking at the Chainlink, obviously we have to mention the oracles. In our case, this is attested oracles, meaning that they run inside of the trusted execution environments, and they provide the attestation to the blockchain smart contracts, and those smart contracts can verify that this is a right. They can trust this information coming from those oracles. So there are a number of variety of different types of oracles that can be built using the Avalon. So one of them, they kind of like just execute the algorithms that is actually too expensive, too computationally intensive for the blockchain to run there, or they, in some cases, not really practical for the execution, like random generating random numbers. So that is the first class of the potential uses for the attested oracles. Another one, integration with the legacy applications. In this case, trusted executions environment can execute code and data and make sure that both code and data are protected, and the allowed information is actually going to be provided to the smart contracts on the blockchain. And finally, Avalon can be used to build a trusted intermediary that will connect to the external data sources, get this information, may aggregate them, may uh, each trusted execution may attach to specific sources. This is really application specific. But the key here that there is an extra protection and extra assurance in this model because of the T is actually can uh, provide the attestation information and the proof of the execution to the blockchain smart contracts. And since we all affected by the COVID-19, it's hard to not create an example of the use case that involves the COVID-19 tracking, especially since this use case is actually very nicely fit into the trusted execution environments. And by the way, there are real companies, the real products that people building using the trusted execution environments already. What I'm going to describe here is somewhat a hypothetical use case. I don't think that anybody builds it exactly like that, but fundamentally the concept stays the same. So individuals may report or auto-report their tracking data. And the tricky part here that when the people report the data where they move and these data recorded somewhere in the service, it's kind of hard to trust that these data not going to be incorrectly used or even abused by the uh, hosting company, or especially by the potentially the attackers who would attack that hosting company. And that is where the trusted execution environment comes to play. It processes the data, it stores them in a encrypted tracking database, and only trusted execution environment that actually can see the data in clear. The second set of data comes from the hospitals. They report infection cases, again, through the trusted execution environment. And then they record it also in the encrypted tracking database. And finally, let's say the CDC runs, or some other authority runs the reports against the encrypted tracking database to get the list of the people who may be potentially infected. Even in this report, it's very important. All this authority, CDC in our case, can know is that it knows the names of the people that may be affected. It doesn't know where they potentially can be affected. It doesn't have access to the actual detailed tracking information data provided by the individuals. Finally, another set of the trusted execution environment, it actually reports the data to blockchain. It reports the proofs of the data recorded, it reports the statistics, whatever makes sense to share on the blockchain. So this is the last use case I have to describe what kind of use cases we're looking for to address. Now I would like to talk about why we're actually running this project, what we're trying to do, what the key objectives we're trying to address. So first of all, the asynchronous model of the execution. When I was talking about the attestation, you saw that there is a link, direct link between the remote party. There was direct link between the remote party and the trusted execution environment. And this is how many environments, trusted execution environments, is actually designed to work. Unfortunately, that does not work for blockchains because blockchains are asynchronous by nature. That is why we implement the specification, trusted compute of chain specification by EE, that is actually describes the mechanism how we can submit results, how we can report available workers, and how we can do this all in the asynchronously without relying on the direct link between the requester and the processor. The another the important part that we have is the cross-TE execution and access to the external data sources. In reality, it's relatively straightforward to do the execution on the one in the one trusted execution environment. But if we have multiple trusted execution environments, it becomes much more complicated. And when you saw example about the insurance company quote, that involves many multiple players. Federated learning, that is another example when there are multiple parties, the confidential federating learning, that is multiple parties has to be involved to process the data. So this is another area of focus for the our project, is to make sure that we establish the right patterns and the common code for the cross-TE execution. The important part is scalability and multi-tenancy support. Even the TEs, first of all, a little bit about the multi-tenancy. So the TE obviously provide protection, but at the same time, the code that is actually loaded inside of enclave, not necessarily full of bugs. It's still software. So technically, if we execute the code from the enterprise A and the enterprise B, or customer A and customer B, in the same enclave, there is a possibility that the code may leak data from one customer to another. So the achieving the multi-tenancy using the hardware-based capabilities in the CPU, that is the one of our goals. Another one is scalability. The SGX, for example, is great. It does protect your data. It protects your code. It has a notion of so-called sealed storage. So between the reboots, it can store its keys, for example, in this sealed storage. And it's designed in a way that only code running on the same physical system can read the data, because the keys attached to that particular CPU. Unfortunately, that is problem with scalability. If you want to use something like Kubernetes or OpenS, that is not going to work as expected from the hosting service, because they want to move the workloads freely between the available physical units. And that is another important part that we addressing by migrating these key and the critical data between the physical systems in the secure manner. Now, there are those who already played with the trusted execution environment, those that there are a number of different options that exist on the market that can be used to build solution. The obviously the minimally sized, the solutions with minimally sized trusted compute base is the very important. And you can use the SGX SDK from Intel or Open Enclave to build those solutions. This is great. We do use it for our internal purposes as well. There is one disadvantage of that approach. It's actually relatively hard, and you limit it in the languages that you can use. Typically, you have to write your code in C++. That is why people looking for different options, they don't have the benefits on that small TCP, but they allow either moving the existing application as is, or easy porting of them to bigger environments and the more like traditional environments. The typical examples of them would be Graphene Oaklum or SGX LKL. That is open source options. There are similar options that is actually commercial, like Fortanix or Scone. And finally, there are different trusted execution environments, for example, TrustZone, that is the we would like to support in the our project as well. So that is why that is another important area for us to focus on the being generic, abstracting the specific development environment or runtime that application developers would choose for their product. And one more interesting part is actually addressing the potential vulnerabilities, especially when you use something like as big as the that allows you to run the whole application, a large application, maybe several applications like Graphene, using the Graphene environment. That is very helpful. Unfortunately, there is a possibility, higher possibility for the application bugs and the user errors. And to deal with that, one way to mitigate the potential issues of these errors and bugs is to isolate key management for actual work order execution and improve the overall solution security. That is the fifth objective that we're trying. Zoom admin team is requesting remote control over you. Okay, so oops, sorry. So this is the five the objectives that we're trying to address. So that is the asynchronous compute model, the running in the trusted. Okay, somebody wants to take control of my system. Hello, can you hear me?
Yes, we can hear you perfectly.
Yeah, and somebody asking for the control of the screen. Should I give it?
No, you should just deny. Just say deny.
Okay. Okay, so just to summarize, we're trying to establish a synchronous model using the trusted execution environments and communication across the multiple trusted execution environments, and ensure that high scalability and multi-tenancy support. We want to support variety of TA options and runtimes, and then we want to reduce the impact of the vulnerabilities. Okay, I will move this on side because it's popping up all the time. I don't know if you see that on your screen or not, but I see these
I'm not seeing it. Do you know who the person is who's requesting that from you?
No, it doesn't. It says the Zoom admin team.
Zoom admin team. Okay, well, I would just say deny.
Yeah, well, I do this. It's just copy them every few seconds, but it's okay. So these if it doesn't bother you, that is okay. So okay, now let's move to the architecture slide. It's actually Jake Wright is requesting the remote control of my screen.
Jake Wright. Okay, I'm going to look for him, but do not allow that. Just deny it.
Okay. Okay, so so this is the architecture, at very high level of the Avalon. These so there are three parts really. This is the trusted compute service itself, the requester application, and the smart contract running in the blockchain. So in the requester has two options. They can contact to the trusted compute service either through the blockchain, or they contact directly through the JSON RPC service. And the Avalon provides a connector library that makes this almost transparent to the application developer. Inside of the trusted compute service, we have the registry of the workers. We have the work order queue, and they can be connected to the blockchain through the blockchain connector. And the blockchain can be Ethereum, Fabric, or we can extend that model to any other additional blockchain. There is the JSON RPC listener, And the important part, within the orchestration box, we run the workers. Workers include the work order processing enclaves, like I said before. Those are actually that execute the actual workloads. There are key management enclaves. They maintain the key, and private keys are known only to those enclaves and not to the work order processing enclaves. And there is a mechanism for accessing the external data. I show that in the gray, we do not have that, but we have plans to extend the Avalon to support additional trusted execution environments like ARM Trust Zone and the other trusted compute options, that is the zero knowledge proof and MPC. And the finally, I would like to point out that there are two models of the communication. They done for the particular reasons, because technically all communication can be done through the blockchain, but in the real world, there are situations when we don't want to so unfortunately they come in and I have to click on them. So the so in real world, you sometimes want to have a direct communication with the trusted compute service from your application to avoid sending too many requests to the blockchain, or because you have to send the data in your request that cannot be shared on the blockchain.
Excuse me, sir.
Yes.
Wait, hold up. Oh, never mind. My bad.
Yeah, this is a Denver Hyperledger meetup. We'll have this for the next 24 minutes.
Okay.
So please disconnect or join us if you want to learn more about Hyperledger Avalon.
Yes, but can I please have some fruits?
No, we're going to keep moving here. Okay, go ahead, Eugene.
Okay, so now let's look at the flow diagram. And the in this flow diagram, the important part at the high level to understand that there are two distinct phases. One of them is the establishing chain of trust, and this is really the registration, so and discovery of the workers. So the blue boxes actually represent the trusted compute service, and the green stuff represent the trusted code running inside of the enclave. So at this time, the trusted compute framework would create the worker, and it would register that worker on the blockchain. And then the customer or the requester would come and make a lookup and find out the right worker for execution. It should be noticed that after the worker was registered, it actually does not have to exist. It actually can be shut down until the right work arrives. So during the second phase, the work order processing, the requester submits a work order. The work order is actually eventually gets to the trusted compute service through the blockchain. And in this time at this state, the dispatch the to the pool, to the worker for processing, the right worker can be started if it's not already running. And the work order going to be processed. It may require access to external data on other TE. And the I want to point out the application of workload is actually in this case is doesn't have to understand all these details. It's really involved primarily in the only the application specific logic. All these integrity enforcing, registration, the confidentiality enforcement, all these is transparent to the application developers. And finally, the result arrives to the requester, and the requester can process the results. So, okay, these coming a lot. Who is Richard Summers? I keep getting the request for the screen from control from Richard Summers.
Yeah, here's what I would say, Eugene. Let's just ignore any request for anybody to take over control of the screen. You have the meeting for the entirety until we turn it over to Keenan if he would like to present.
Okay, got it. So, a few words about the chain of trust. So the, as I said, that we rely heavily on the attestation information provided by the IAS. And it was provided by the hardware. And there are two options related to SGX. Without going to details, there is an older option, the IAS, that has been around, and there is a new one called DCAP, data sensor data center, the application primitives, attestation primitives that provide the proof of the enclave that being executed. And what we actually rely, we rely on the field called report data in the attestation report. And that report data is actually includes the hash of the verification public key, corresponding private key, and the stored in the enclave sealed storage and available only to this enclave. And the encryption public key signed by the verification by the signing key, and it can be verified with the help of verification public key. And then the encryption private keys also kept in the sealed storage. That is actually how we extend the attestation model for our purposes. And when the request is made, in this case, the requester generates one-time symmetric encryption key. It encrypts the data with that symmetric key. It calculates the hash of the request, and then it actually encrypts that hash as well, and encrypts the one-time symmetric key with the asymmetric key provided by the worker. And this request now can be sent. It also can be signed by the requester. And during the work order processing, there happens the kind of like the processing happens in the reverse order. The worker inside of enclave decrypts the encryption key. It verifies that this is the integrity of the worker by checking the hash of the message. It may verify the signature if it's provided as well. It decrypts the actual data using the key and processes the work order, and then it actually encrypts the result using the same one-time key, and it calculates the hash value for the response, and the signs the result with its signing key. So that is actually how it ensures that the requester can verify that the results is actually indeed received from the right worker, intended worker, using the right algorithm. So the few words about the architecture we have. This is kind of like one click down the architecture of the Avalon that includes effectively these three layers: the front end that has listeners for the gRPC and blockchain connectors. In the middleware, we run the key value storage handler that effectively maintains the worker directory and work order queue. And we have the work order queue manager. And this slide shows the so-called pinned workers. Each of them is actually can be started in only one instance and always attached to a particular physical platform. In some cases, it can be useful, but as we talked about the scalability before, that is not optimal mode for many of the hosting services. They would like to have what we call worker pools. And the next slide shows the changes to the architecture that done in order to support these worker pools. So the worker pools include two types of enclaves, the WP, which is actually stands for the work order processing enclave, and there is the key manager enclave. Those is actually they manage the key, and they, like we discussed before, they actually separate the work order processing from the managing the private keys in the key enclave. So that ensures the security of the application. And the important part, we do not invent our own orchestration mechanism. We pretty much just provide necessary building blocks that would allow to use the existing orchestration options, Kubernetes in particular, to make sure that the workers can be scheduled practically in the same manner as the regular non-trusted workloads or non-confidential compute workloads. So that is the at the high level, the architecture of the Avalon. And I think that is my last slide. Yes, so this is thank you. I appreciate the opportunity to present Avalon to this community. And please get involved with the Hyperledger Avalon. We have the GitHub, we have the tutorial. It's pretty easy to build it. There are a number of links and documents in the last link, including the number of videos that you can, in addition to this presentation, to watch and see how to, for example, to quickly install and use Avalon for your projects.
Yeah, great job, Eugene. I'm going to go ahead and start my video here. So let's go ahead and open it up to the chat and see if we have some questions for Eugene. In the meantime, Keenan, do you want to weigh in and add some additional information here?
No, yeah, thank you a lot, John, for organizing this, and thank you, Eugene, for that presentation. It was wonderful. We got a little bit of time left, so would love to just open it up if people have questions for Eugene and want to learn more about Avalon.
Yeah, I guess I'll kick it off and just ask Eugene about, Eugene, it looks like you have a great environment here with the trusted enclave. What about usage in production? Do you have any proof of concepts or usage for Avalon out there?
So we have a number of POCs that is being worked. So the Avalon is technically a work in progress. We haven't reached the active stage at Hyperledger, so we in incubation phase. We do have a number of companies that building products based on the Avalon already. Many of them do not talk about that publicly yet. But there are example would be the Baidu, for example, already announced their plans. There are a number of others who actually do the prototypes and other work. For example, Wipro has actually made the very good proof of concept and I think even pilot for the supply chain. They call this cold chain. It was actually presented at the DEF CON 5 last year, and you can sorry, it was presented actually at Hyperledger Global Forum this year in March, and the link, the last link on this website is actually includes the I think videos that is actually you can see the presentation of that solution as well.
Okay, perfect. I think there's one question here about integration between Fabric and Hyperledger Besu. Do you have any comments around that?
So is this question about the integrating them individually or integrated between them?
I would say it looks like it's a bridge between the two of them.
Okay, so we do not have immediate goal to bridge the different type of blockchains. That is not the objective of the Avalon. But we do have connectors that connect to both, to the Besu and to the Fabric. So depending on your application, if you have an interest to link them together, you can have the trusted execution environment that is connected to both. To a trusted compute service with multiple actually trusted execution environments that can be connected to both Besu and to the Fabric. And you can, inside of your workloads, inside of trusted execution environments, you can actually do the necessary processing to make sure that you exchange the data between two different blockchains. So what I would say that it's not our goal to work on the cross blockchain solutions, but Avalon definitely can use as a building blocks to create such solutions.
Okay, perfect. Other questions, if you want to go ahead and post those in the chat. One thing I'll ask you about, Eugene, is really the large consortium of companies that are supporting this. So to me, it looks pretty universal as far as, you have Consensus, you have the Enterprise Ethereum Alliance, you have Hyperledger, and you have a lot of other major companies that are developing blockchain solutions like IBM, Oracle, and Microsoft. So it looks like, really the level of support for this project is almost universal. Maybe you could talk a little bit about that type of support.
Yeah, we definitely have a lot of the interest from the completely different companies. We also have support from the two types of communities, both of them part of the Linux Foundation. So one of them is obviously Hyperledger Avalon, and we talked about that here. So we have the number of companies is very actively involved in this project. So the Chainlink, one of them. We also have the very good working relationships with the company iExec. We work closely with Santander. There are a number of companies in China that has a lot of interest in what we're doing. We also work with another community called the Confidential Compute Consortium. It's a newer organization within the Linux Foundation that focusing specifically on confidential compute. And obviously the Avalon kind of belongs to both of them. We even made a proposal to split Avalon into two parts and maintain the blockchain related part within the Hyperledger, continue to use the name, but take the confidential compute part, the trusted compute part, and actually maintain that in the confidential compute consortium as a project. We reviewed that, our proposal with the technical advisory committee and the confidential compute consortium, and it was accepted as the project there. So at some point we may split the Avalon in two different projects. One of them will going to keep in the Hyperledger, and we're going to focus on blockchain specific
Sir?
usages. Yes.
Good morning. I have a question. This program is brand new. I mean, this is new.
Oh my God!
Because, oh, wait. Because I was.
Get off the toilet.
Okay, Eugene, sorry about that.
All kinds of boo-boo.
Interesting.
Yeah, it's one of those things that I have to remove and report these people. So whenever I see them pop up, I had to take that out. So let's just move on, Eugene. Nonetheless, I have a question here from Mohammed that's a great question. He asked a question about your Avalon objective slide, and you talk about other trusted execution environments, trust zones, and he wants to know what kind of improvements from a privacy and security perspective are expected by using an ARM trust zone rather than an Intel SGX. So I guess he's trying to compare two types of trust zones.
So to me, the primary goal would be where we deploy the trusted execution environment. The Intel SGX trusted execution environments runs primarily on servers. And when you have your execution in the data center, that works completely fine. But if you need to ensure the data, the kind of like establish the chain of trust all the way to the endpoint, that is where the trust zones actually comes to play. So for example, if you use you want to have a trusted sensors uh, running, for example, in containers and shipments, that is actually would be very helpful for supply chain to use the trust zone to send the data encrypted and this enforce the integrity. That is actually where the trust zone can be used as the complementary to the, for example, SGX trusted execution environment. So we would be able to establish the same confidential compute all the way from the endpoint to the data center.
Okay, perfect. Looks like we have another question from YouTube here. Where do you see the industry in 5 years' time, given the current situation with COVID? Would that be a trigger for mass adoption of blockchain?
I think that in 5 years, we're going to see more both the confidential compute and blockchains. And I think that they kind of created for each other, because confidential compute allows you to do the trusted execution within the one entity, kind of like efficiently, compared to the replicated execution on the blockchain. But at the same time, blockchain provides the same important benefits like the immutable or hard to modify the logs that is actually have established a different type of trust. And the COVID-19 definitely, we see already that as a trigger. I presented this use case, the COVID-19 use case. I didn't really come up with this use case on my own. By preparing for this presentation, just realized that I see that people already doing that. They're doing that very actively. And that is the pretty clear indicator that where the blockchains and the confidential compute comes together and solve the real world problems. And I think that in 5 years, I would expect that close to 50% of the execution is going to happen in the with help of blockchain in the confidential compute environments, especially as we going to see the growth of the processing at the edge. And edge has even the additional concerns, security related concerns, because a lot of execution will happen in less the protected environments that the typical cloud service provider data center.
Okay. Another great question here from Armando. He was asking about, I know that Avalon is looking to reinforce confidentiality in the transactions data, but he was asking about if the establishment of trusted environments means more participants, intermediaries, and instances in the ecosystem, and therefore it's going to affect the performance and the efficiency of the transactions. So maybe you can talk a little bit about that.
I don't think that it's necessarily the case. The number of intermediaries, it's really the matter of the design. When I was talking about this is definitely important consideration. I agree with that. Does it really, if we go naively about that, yes, it will cause the extra delays. It will cause the extra cost. But if we pay attention to that, and remember the second objective for us is actually focusing on the cross-TE communication. This is all really about the getting the benefits of the confidential compute joined with blockchain without the introducing unnecessary overhead. So yes, this is concern. I think it's addressable. It's probably will take few years to fully address that, but over the time, we're going to find the right methods and right ways how to handle that efficiently.
Perfect, Eugene. Well, we're coming up on the top of the hour here, so I really appreciate your wonderful presentation, Eugene. Anyone has any questions, feel free to follow up with Eugene through the Hyperledger Avalon group. And Keenan, I really want to reach out and thank you and Chainlink for joining this as well and being a great part of Hyperledger Avalon. And I look forward to connecting with everyone soon for our next Denver Hyperledger meetup.
Thank you, guys. I appreciate the opportunity for our team to present the Avalon at this meetup.
Yeah, thanks a lot, John, for helping organize this, and Eugene for your presentation. If anyone has questions about Chainlink, feel free, you can reach out to me. I'll drop my email into the chat here, and feel free to reach out anytime. And then look forward to doing future meetups together and working together.
Okay, everyone, have a wonderful day and thank you very much. Take care.
Thank you. Bye-bye.